Okay, so one thing to talk about today is gravitational potential energy. You'll see in the book, it's PGE. Actually, I'm sorry, GP.
Well, it's not, the volume's not working. I can't hear.
Oh, let me go ahead and fix that really fast. That reminds me, if you can't hear me, just exit and come back in. I'll have to tell Catherine that because she can't hear me. But if you ever have that issue when you come in and you can't hear somebody, just leave the meeting and come back, and that will fix the problem. Okay, so GPE, the equation for that, we've already looked at this before. It equals mass times G times H. So again, M is mass, G is 9.8 meters per second squared. And then H is the height. Now that is a little bit arbitrary, and the height really is up to the scientist as far as what's useful, because it is relative and it can vary. So for example, if you have a ball on the table right here, you might want to say, well, height is from the tabletop to the floor. Yeah. I got a new trackpad. I'm still trying to learn it, but hopefully my drawings will get better as I learn how to use this. Okay, so that's supposed to be the floor. And so height could be from the floor to the tabletop, and that would make sense in this context. But let's say instead you have this setup. Where you have the ball on the table, but it's right over a chair. So if you think about what can happen here, the ball could hit the chair. I'm going to erase that to make it easier to see. Well, that's even worse, but anyway, this is supposed to be a chair right here. It's supposed to be a table. So the ball could go from this part of the table to the chair. And so we could define height that way, from where the ball would go from the tabletop to the chair. You could also define height like we did up here, where you could say, well, H is from the tabletop to the ground. So either of those would be valid. But in this context, this would make more sense. It'd make more sense to say this would be the height, because that's really where the ball is going to fall. It's going to fall from the tabletop to the chair. And so gravity would have the potential to move the ball from here to here. The ball realistically would not move from the tabletop to the ground. Now, if we're on that side, yeah, it would, or if it were up here. But in this context, it wouldn't. So it really is based on the situation as far as what height you would use. It's going to be usually pretty clear what height you would use, but just know, the main thing to know from this is that the height is relative, and it's up to the scientist to choose where to have the baseline. So we would call the zero height the reference point. On this side, this would be the reference point, where height would be 0 on the ground. Over here, the reference point would be the chair. And that's where we call height 0. A reference point is defined as the place where you have 0 height. And by definition, if you have 0 height, you have 0 potential energy because 0 times m and g is equal to 0. So PE is 0 when height is 0. Can you all see that very bottom line right there?
Yeah.
Okay, good. Because I can't tell in my screen if you can or not.
Oh, you ain't got no leafy ones? What the heck is color your eyebrow? Green.
Okay, so everybody have this down?
Yes. Yeah.
Yes.
So when I got on my same thing like that. Every day I've been.
Okay, so going back to the example again, let's redraw those two things and look at these in one more context. So you have the tabletop, you have a ball on top of the table. And over here, we define height as to the ground. So the reference point is the ground. And so at this point, height is 0. And we define height like that. So if you were to have the ball move downward, and the ball were to go from here to the ground, let's say height equals 1 meter. We could then find the energy that the ball moves through as it goes down to the ground. We would need to know the mass of the ball, and then we could solve for that. Just to make it easy, let's just say the ball is 1 kilogram and the height is 1 meter. We could then calculate potential energy by using the equation mgh, so 1 kilogram times the height, 1 meter, times 9.8. So that would give you 9.8 joules. So if you multiply kilograms times meters over seconds squared, that would give you, I'll just go and write this out down here, kilograms times meters over seconds squared, which would equal kilograms times meters squared over seconds squared. If you remember, kilograms times meters over seconds squared equals a Newton. So we could replace kilograms times meters over seconds squared with a Newton. At that point, you would have 1 meter left over. And so a joule could be written as either newtons times meters or as this unit right here, which you usually don't use. So the units right here we can see will be written as kilograms times meters squared over seconds squared. You can rewrite that as kilograms times meters over seconds squared times meters. Kilograms times meters over seconds squared equals a Newton. We have 1 meter left over. So we have newtons times meters, which equals a joule. So that's how we get joules from this unit right here. Now it's all over the place. Does that make sense? Do I need to re-explain that, or do you all understand how we got that?
That makes sense.
Okay, let's go ahead and move on. So in that case, when the ball moved down, we say that it gained 9.8 joules of energy. Gravity did positive work on the ball. It got faster, it gained energy. So you gave energy, gravity gave energy to the ball by pulling it downward and accelerating it. Now, it could also happen is you could move the ball up and work against gravity. And if you pull the ball upward, you are now doing work against gravity. You're doing work on the ball, giving energy to the ball, but you have to fight against gravity to do that. So if you move the ball from the tabletop upward, and we'll say that's also 1 meter, you could say that you have given 9.8 joules of energy to the ball, because energy change would still equal m times g times h. Height is 1 meter. The ball we said was 1 kilogram in mass. So in this case, you gave the ball that energy, 9.8 joules of energy you gave to the ball. In the other case, when the ball fell down, gravity gave energy to the ball in that situation. So if you move the ball from, say, here to here, your reference point, we are assuming that height 0 is right here. So we would call the tabletop our reference point. When the ball's on the table, we're saying that's at height 0. So in the earlier problem, we defined height 0 as the ground, because the ball is going from the tabletop to the ground. But in this problem, we said, we started right here and it moved upward 1 meter high. And so we're calling the tabletop height 0. Does everybody have this down? I was going to erase it all.
Yeah.
So if the ball starts on the tabletop and we call that height 0 right here, we would say that originally it had no energy. Let's say the ball then moves from the tabletop to the ground. Well, if we defined the tabletop as height 0 and it moves down, let's say it moves down 1 meter, it's now moved down -1 meter because we called the tabletop height 0.
You can have negative joules or joules or whatever.
You can, yes. So negative just means how it's being transferred. And so
Okay.
it's just saying which way the energy is moving. So if a reference point is the tabletop, you're now going below height 0. So that would be -9.8 joules of energy. So again, it's arbitrary. The magnitude wouldn't change. It's still 9.8 joules of energy that has transferred. That is always constant. But the beginning energy is different, because if we call this height 0, then we're saying that this ball has 0 energy to begin with. But if instead we had what I showed you before, where the ground is height 0, then we would say that the ball right here has energy that's equal to 9.8 joules, because it's 1 meter off the ground, and we say that this is height 0. It's now 1 meter above that. So up here we say it's 0. Down here we say it's 9.8. So you can define the energy it has in different ways, but what matters is not the starting value, it's the changing value. And so that's what we're concerned about. And in both cases, whether we define the height from the tabletop or from the ground, we still get 9.8 for our answer. And that's what we're concerned about in these problems, is the change in energy, not total energy. Because total energy is relative. It's based on something else. It's based on a baseline. And the baseline can change. Does that make sense?
Wait, doesn't it kind of matter because one point is negative and one's positive, like from your reference point? If you start in a certain area, it'll be either negative or positive.
Yeah, that's a good point. And we
Nice.
would deal with magnitudes in that case, because you're right. You know, we have moved below the reference point, so that is the negative value. So we would just deal with a magnitude. We wouldn't deal at the end with negatives or positives. We would just say, in both cases, the ball has gained energy because it's moved downward, right? It's accelerated. Now, it's lost one kind of energy, though. It's lost potential energy. So it went from having energy that was, well, in this case, it went from 0 to negative 9.8 joules. So as the ball goes from here to here, it has lost potential energy. That's why we have a negative right there. But it has gained kinetic energy. So while the ball has lost negative 9 potential energy by moving downward, it has also gained kinetic energy. It's gained 9.8 joules of kinetic energy as it moves down. So if you decrease the height of the ball, it will decrease potential energy. So PE is negative 9.8 because it's lost that energy that's potential, but it has gained kinetic energy because it's increased its speed. So energy has been transferred from one to another.
Okay, that makes sense. Thank you.
So is that clear for everybody? So again, energy has been lost as far as, you know, if you go from a higher to a lower height, that energy has been lost. But you gain energy if you increase speed. So while the ball moves downward, it loses potential energy, but it gains kinetic energy as it moves down. Okay, let's look in your book at a problem on page 290. If you have your book with you, it says that you lift a 7.3 kilogram bowling ball from a storage rack and hold it up to your shoulder. The storage rack is 0.61 meters above the floor, and your shoulder is 1.12 meters above the floor. So there's A, B, and C on here. The first question is, when the bowling ball is at your shoulder, what is the bowling ball's gravitational potential energy relative to the floor? So I'll show a picture, and the book has a picture of this, but I'm going to draw in case you don't have your book with you.
Wait, what page is that, Miss Holly?
Page 290.
Okay, thank you.
Okay, so you have this bowling ball rack, and there's balls at different heights along here, but they're getting a ball at this point. And they say that the ball from right here is 0.61 meters above the ground. And you're lifting it from the rack up to your shoulder. It says that the shoulder is a height of 1.12 meters above the ground. And they're asking, what is the bowling ball's potential energy relative to the floor? So for A, what we need to find is the energy from here to the ground. So we use this equation to do that. They give us the bowling ball's mass in the problem. It's 7.30 kilograms. So that goes in for M. G is always 9.8. Height is from the bowling ball to the ground, 0.61 meters. So we just multiply this all out. Just make sure you have the right units. Always be in kilograms, meters, and seconds. So that would give us 80.1 joules. Each of these have three, actually, sorry, this one has 2 sig figs, in which case we really should just have it as 2 sig figs. So we wrote it as 80, that would give us 1 sig fig. So we have to write it in scientific notation. Now, you can also write it as 9.80. So if you were to include the 0 right here, I think the book does that, then it would be right to report it with 3 sig figs. But I had only written as 2 sig figs, and so I should report it like that. But if you wrote it as 9.80, then it's fine to report it as 80.1. Okay, for B, it's asking, when the bowling ball is at your shoulder, what is its potential energy relative to the storage rack? So in that case, what they're asking for is energy. So the ball is up here, and they're asking for energy from this part to the storage rack. So we need to know the change in height from the shoulder to the storage rack. So all we care about is this right here. That's what we have to use as height. It's the difference between 1.12 meters and 0.610 meters. So if we were to do 1.12 meters minus 0.61 meters, that would give us a difference between these two heights, and that would give us a height right here, which it moved through to be pulled from here up to the shoulder. So we do 1.12 minus 0.61, and that gives us 0.51 meters. So at this point now we can use the same equation we used up here. So the mass is 7.30 kilograms. G is 9.8. And then height 0.51. So that would give us 36.5 joules. And again, and if we're using 2 sig figs here, we have to change that. If you put a 0 in here, keep it as 3. So 37 joules would be the right way to report that if I have 2 sig figs. And also there's 2 sig figs right here as well. So in either case, even if you put in a 9.80, there's still 2 sig figs for this one. So we have to keep it as 37. Does everybody have this down?
Yeah, Miss Holly,
Yes.
for A, the potential energy, is it supposed to be 8.0 times 10 to the first? Because that would be 800 joules there.
Exactly right. That should be first.
Yeah.
Yeah, good catch. Yeah.
All right. You're welcome.
Okay, anything else? Let's go on to see if you have this down. Okay, for C, it's asking how much work was done by gravity as you lifted the ball from the rack to the shoulder level. So in that case, what they're asking for, so again, we had the rack right here. The ball went from here upward. So it was originally at a height of 0.61 meters. It went up to a height of 1.12 meters. And they're asking, what is the work done by gravity? So as the ball went from here to here, it gained energy. It is a higher height, and so it has a greater potential energy. So it went from here to here, it gained 80.1 joules of energy. So because the ball gained that energy, that means that something else had to have lost that energy. So the work done by gravity would be 80.1 joules of energy if it went, actually I read the question wrong, I'm sorry. That would be if you went, because for A, that was, no, sorry, let's ignore the 80.1. It wasn't 80.1. What you have to use instead, it was 37 from the last problem. So sorry about that. If it went from here to here, it's 37 joules of energy. The 80 was from here to the ground. Okay, so it went from here to here. We found that to be 37 joules of energy from B. So it gained that energy. So the work done by gravity would also be the same magnitude, 37 joules. But gravity is pulling downward. So the force of gravity is directed downwards. Which way is the ball going? Ball's going upward. So we learned yesterday that if the direction is opposite the force, then negative work is done. So if gravity did negative work on the system, we would say that the work done by gravity is negative 37 joules. And we know that because the force of gravity is downward, the ball is moving upward. And so the ball gained 37 joules of energy, but gravity did negative 37 joules of work because it moves downward as the ball goes upward. Any questions about that? Okay, so I'm going to have you work on a few problems today on page 291. Just do 5 and 7.